Ladies and gentlemen, boys and girls, welcome to another lesson of transparent physics. In this lesson, we are going to start a new unit about dynamics. Dynamics is the study of how forces interact with objects to cause changes in motion, or not, depending on how the forces add up. So we're going to start today with a lesson about forces themselves. So in this lesson, we are going to define the idea of what a force is, and spoiler, it does not involve metachlorides. And then we're also going to explain the difference between balanced and unbalanced forces. This sets up a relationship that becomes very important as we move further into this unit. Alright, as we get started on the main course here, I encourage everyone to pause the video and brew yourself a cup of tea. I'm going to take my obligatory tea break right now. That is good. Hopefully you're back with a cup of tea. Let's go. What is a force? Your course might define force as simply as saying it's a push or a pull. Hey, and that's fair. I'm going to tease that out a little bit to say it is one object pushing or pulling on another object. And I like this phrasing better because it draws in the idea that there has to be two objects interacting. You can't have a force if there's only one object. Two different things need to interact with each other, and this is enhanced further when we talk about Newton's laws. So it's a good framework to get started with, recognizing that we always have those two forces. The problem with this definition is that you can make it a little game for yourself to try to define what a push or a pull is without actually incorporating the idea of the word force. I think basically we're just defining force with synonyms for force, and maybe that doesn't get us that much closer to an understanding. Another way of looking at it is saying that it's an agent of change which can alter motion. If you know a little bit more about how forces work, this is actually a pretty tight definition. But in the same regard, it's also kind of mysterious and a little vague. What is an agent of change? Coming this fall on Disney Plus, I guess, Agents of Change. And when it comes down to it, people who know realize that force is a little bit hard to nail down in terms of what exactly it is. As Richard Feynman says, if you insist on a precise definition of force, you will never get it. So I guess we're just kind of whistle past the graveyard on this one and just go with the main idea that it's a push or a pull acting on one object from another object. All right, let's get down out of the clouds a little bit and talk about the nitty-gritty of how force actually operates. Forces are a proud member of the vector family. Vectors, if you remember, are measurements that require both magnitude and direction to be fully described. The magnitude of the force is the strength of the push or the pull. The harder the push is, the harder the pull is, the larger the magnitude. Magnitude is measured in what we call newtons, named after, of course, Isaac Newton. We're going to talk a little bit about the base units for newtons. Newtons is a derived unit that is based on a collection of smaller units combined together. So you can see some familiar friends here: kilograms, meters, and seconds squared. In a little bit, not this video, but in a later video, we'll talk about where this comes from. If we are interested in the value of a Newton, generally speaking, if you can imagine a reasonably decent sized apple in your hand, that's about a Newton of force. So it's not a crazy amount of force, but kind of apple-ish. And if a vector has to include a magnitude and a direction, then the idea is that the push or the pull needs to be acting in a certain direction. Think of it in the idea that if you're pushing somebody, you have to push them in some way. You can't just be like push and like have no direction associated with it. You're always pushing them somewhere. In that regards, when we're talking about one-dimensional dynamics, which is where we'll start, again, we're either looking like left, right, up, down, forward, backwards, things like that. And this can be represented just with a plus or a minus. If you push them to the right, it's a positive. If you push them to the left, it's negative. If you push it up, it's positive. If you push them down, it's negative. And that's a great way to get used to stuff. Later on, you'll be talking about forces in terms of angles. So you might have a force at 45 degrees and a force at 137 degrees, things like that. It just gives us more flexibility in how forces interact with objects. So for example, if we go back to the one-dimensional considerations, you could say a force would be plus 14 newtons, and that would be a good example. So armed with a framework for what a force is, let's talk about how forces start to hang out in groups together. And this brings us to the idea of balanced versus unbalanced forces. We'll start with balanced forces. In general, when we're looking at the impact of forces on an object, we have to look at all the forces together that act on the object, and we'll break it down in a certain direction. So we'll just pretend all the forces right now are horizontal or all the forces are vertical. But again, it can be both at the same time. If, say, we're looking at an object and the forces acting to the left and acting to the right are, nobody's winning, then the forces are considered to be balanced forces. When we look mathematically at that, balanced forces have the same magnitude acting in opposite directions, and this is regardless of the total number of forces on each side. I could have one really big force tugging to the left and three smaller forces tugging to the right, and those could still be balanced. It's fine. The number of forces is not what we're balancing. We're balancing the total magnitude that those forces provide on either side. So let's take a look at three different scenarios involving balanced forces. Scenario number one, a pet raccoon sitting on the sofa, and when we're looking at the raccoon, there is a force acting up on it. The sofa is pushing up on it. Gravity's pulling down. So if we were to express that in terms of a more graphical representation, arrows make an excellent way to describe forces because the length of the arrow can be considered to be representative of the comparative magnitude, and the direction obviously would indicate the direction. Since these arrows are drawn to the same length, the magnitude represented is the same. And also, if you notice the way I have this written, we've got a force on the raccoon by the sofa. So this notation draws home the idea that every force is an interaction between two objects. The sofa is pushing up on the raccoon and gravity is pulling down on the raccoon. And one other thing to note very briefly, when I'm saying gravity, really it's the Earth. The Earth is the object that's pulling down on the raccoon. But that tends to get confusing to phrase it that way. So I'm going to use a bit of a simplification, and we're just going to consider it to be gravity. Gravity is pulling down. But really behind gravity, the object is the Earth. The Earth is pulling down on the raccoon. Okay, secondly, we have a pug pulling on a toy from its owner. And we are actually not going to focus on the pug here. We are going to focus on the toy, although as hard as it is to stop looking at the pug, we are going to be interested in the toy that's between the owner and the pug. And we're going to pretend that we're looking at this from a side view, so that to the right, the pug is pulling on the toy, and to the left, the hand is pulling on the toy. And you can see here that there is a force on the toy by the human acting to the left. There is a force on the toy acting to the right by the pug. The arrows are the same length, which indicates that whatever the force is, I don't know what a decent pug can pull with, but they are balanced forces. No side is winning. And the last one, what I want you to do is focus on the part where the parachute is dropping with the bottle. And an assumption that some people make when you have balanced forces is that the object can't be moving. The raccoon's not moving, there's balanced forces acting on it. The toy is not really moving left or right, there's balanced forces acting on it. But the bottle is dropping downward. And a lot of people assume, well, if the bottle's dropping downward, there needs to be a downward force on it. We're going to tease that out a little bit later when we talk about Newton's laws. But you can actually still be moving and your forces be balanced, just no side is winning. So in this case, when anything on a parachute has reached what's called terminal velocity, whatever the weight of the object is acting down is balanced by the force of the parachute acting up. So in this example, There is a force acting up on the bottle from the parachute, and there's a force acting down on the bottle from gravity. And those balance each other out so that as the bottle's falling, it's going to fall at a constant rate. Again, we're going to talk more about that nuance when we get into Newton's laws, but that's something I want to try to just debunk right now. You can have balanced forces and still be moving. Okay, on the flip side, I don't know, I think we've done a lot of the groundwork, so this will be kind of quick. If you have one side winning, then it's unbalanced forces. Now, when we're talking about one side winning, sometimes the temptation is to casually refer to, which force is the unbalanced force. Be cautious about that, because the idea is that the only way that you get unbalanced forces is by taking a look at all of the forces acting in a given direction, either horizontally or vertically. Now, yes, if there is just a single force acting on the object in that direction, it is alone and it is the unbalanced force. And I'll show you an example of that on the next slide. But if you have multiple forces acting on the object in a given direction, then you can't really isolate one of them as the unbalanced force, because it's the sum of all of them that mean that you are unbalanced. So you could refer to it as an unbalanced force, but maybe not the unbalanced force unless it is the only force acting on the object in that direction. Okay, so let's bring on a trio of examples in support of unbalanced forces. So first we have the 90s classic movie Clueless with Alicia Silverstone playing the role of Cher, and even though she's the most colorful object in the screen with her yellow blazer, we are not actually really want to pay attention to Cher here. We want to pay attention to the guy that she's pushing. The idea, and I don't know if he's a major character, if he's an extra, I don't know about who he is, but the idea is that she's pushing on him to the left from our perspective, and maybe there's some force between maybe his shoes and the ground that would keep him from sliding to the right, but the force that she exerts is much larger, and he accelerates. We'll talk more about that when we get to Newton's laws as a result of the forces. And while we're here, I just want to very briefly draw attention. Again, I've never watched this movie. Maybe in the comments or something like that. Is this guy in the background here important? He looks like an extra that is trying super hard. I don't know. He's got like a book and like a water bottle. I know he just looks like a very well-developed extra. I don't know. Maybe they're all like that in California. But in any case, I'm curious about that guy. I wonder if he has a bigger role in the movie than just some guy walking in the background. Next up, turtle being pushed into the water. And again, we are not actually interested in the push itself. We're interested in the fall. So we're going to treat the turtle just as he loses contact with whatever this platform is and he's falling downward. And this is an example where the unbalanced force is literally the unbalanced force. There's no other force acting up on the turtle. So if there's only a force acting in one direction, it is automatically an unbalanced force because there's nothing else to balance it out. So solo forces are automatically unbalanced forces. And then finally, we have a group of individuals pushing on a car, and as they're pushing on it, you can tell it's kind of hard. There's some resistance maybe within the car itself. We'll just consider that a generic term as friction. And even though there is a force resisting their push, the people exert a larger amount of force, and the car, their push wins, and the car is going to accelerate to the right. Again, we'll talk more about what that means when we get into Newton's laws themselves. So in all three instances, the forces are unbalanced and the objects respond accordingly. Okay, that brings us to the end of another lesson. A couple closing thoughts real quickly. First of all, it is essential moving forward that we have a good understanding of balanced and unbalanced forces. Balanced and unbalanced forces help determine the motion of the objects, which is the entire point of dynamics, is to explain why objects are moving the way they do. And it all drills down to balanced or unbalanced forces. And for now, we will be focusing on one-dimensional forces. So all the forces are going to be horizontal that we're interested in, or all the forces are going to be vertical. But it doesn't have to stay that way. Probably in your course, as you move forward, you're going to be looking at forces in the horizontal and other ones in the vertical at the same time. The same object, same time, has both vertical and horizontal forces acting on it. And just one seed to plant right now is, just because the forces are balanced in the horizontal direction doesn't mean they're balanced in the vertical direction, and vice versa. You got to look at each direction independently, but more to say about that when it is time to do so. Okay, as always, if you found the content of this video to be useful, consider giving a click to the like. If you have any questions about what was in the video itself, you could leave a comment, or if you know what was up with that guy in the Clueless clip. Is he important? I don't know. I really feel like he is. And then finally, of course, subscribe if you want to keep in touch with whatever we're putting out, the latest and the greatest in introductory physics. As always, I appreciate your time and thanks for watching. I hope I've made things a little clearer for you on this lesson of transparent physics.